Okay, let's talk through some of these homework problems. So let's consider whether each of these things refers to a force or not. So the energy used to power a radio, not a force, it's energy. Force is a vector. Light from a spotlight. Light is not a vector. The friction on a sliding puck, that's a force. You're going to apply a force onto a puck to stop it. Attraction of a bar magnet to another, yep, magnetic force. Inertia of a moving car, that's mass. The pull of gravity on a helicopter, that's a force. The tension of a stretched spring, force. Heat of a campfire, not a force. And the push of a foot on the floor, definitely a force. Now, this heat of the campfire and the light from a spotlight, don't overthink it, because light, we will learn, does apply a force called radiation pressure, and heat is technically also applying a whatever. But usually light will be, in terms of luminosity, will be brightness, or heat from a campfire will be joules, and so not a vector. All right, so Lucy boards a crowded bus. As it sits down at the station, there are no available seats, so Lucy stands in the center aisle next to a support pole. As the bus starts moving forward and picks up speed, Lucy holds the pole tightly to avoid falling over backwards. While the bus is speeding up, what is the direction of the total force, if any, on Lucy? So the car goes forward, right? So she has to hold on to the pole to keep her from falling over backwards. Now, why would she fall over backwards? She would fall over backwards because the ground, the bus is pulling forward and her head is not attached to anything, so it would want to stay put. So the bus would go forward, pull on her feet, and push her feet forward, and her head would fall backwards. So while the bus is speeding up, what direction is the total force of any on Lucy? Well, if she's holding tightly while it's accelerating, then it should be forward with the bus. As the bus drives down a straight road at a constant speed, Lucy has no trouble keeping her balance because the total force on her is zero. Constant speed means no acceleration. No acceleration means no force. F equals ma. If acceleration is zero, which is what you have with constant speed, then no force. Bus comes to a sudden stop at a red light, and Lucy grips the pole tightly to avoid falling over forward. During this time, what is the direction of the total force, if any, on Lucy? It's going to have to be backwards because that's what's slowing her down to decelerate her. Okay, so even though when you grab on the pole and the bus slams on the brake and you want to go forward, that's you wanting to stay in motion. An object in motion stays in motion unless acted upon by an outside force. So grabbing onto the pole, by holding onto the pole, you're actually slowing down in the opposite direction. The net force on an accelerating object suddenly becomes zero and remains zero. Okay, the net force on an accelerating object suddenly becomes zero and remains zero. In this case, something is speeding up and then suddenly, boom, maintains a speed. So it should continue at whatever speed it was at when the force stopped. In the absence of a net force, an object can be, in the absence of a net force, you have no net force. So you can only be either at rest or at constant velocity. So, looks like, so it looks like we have an option there, either at rest or in motion with a constant velocity. Those are your only two options. Technically, velocity of zero is also a constant velocity. But with no F equals ma, if the sum of the forces, if the net force equals zero, then you have no acceleration, which means you have constant velocity. So in the absence of a net force, an object cannot be accelerating. Okay? In the absence of a net force, no F, no ma, no acceleration. In the absence of a net force, so without a net force, your net force is zero, then you can't be accelerating. If you have no net force, you could be moving with an acceleration of zero. That would be a constant velocity. And you experiencing opposite but equal forces, yes, because you'd have a net force of zero. You could be in motion with a constant velocity, yes, or at rest, yep. Okay, so it cannot be accelerating. elevators decelerate to stop at a floor. So during the deceleration of an ascending elevator, the normal force on the feet of a passenger is blank her weight. So during deceleration of an oh, that was embarrassing. During the deceleration of an ascending, wow, of an ascending. So I'm trying to enunciate the ascending because of deceleration. So during the deceleration of an ascending elevator, the normal force on the feet of the passenger. So normally, let's do a screenshot here quick. So normally in an elevator, if you're just standing here, okay, on a scale, then it'll just read your weight. Okay? Let's think about this. During deceleration of an ascending elevator, so the elevator's going up, but then in order to decelerate, you're going to have an extra force down to slow the elevator down. Okay, so you're going to need brakes on the elevator to do that. In that case, if you can imagine if you stopped abruptly, she would want to stay in motion. So if the elevator decelerated quicker than she could decelerate under gravity, then she would fly up into the air. So during deceleration, the normal force, it should be less than her weight because she would be lifting up into the air as the elevator stopped. And it's kind of like being at the top of a roller coaster and it feels like you're going to fly out of the seat. During the deceleration of a descending elevator, so in this case, she's on the elevator and her weight is down. The motion of this is down, so the acceleration to stop has to be in this direction. So that's going to make the normal force bigger because it's going to push against her and add up the weight, and so the normal force is going to have to compensate for the deceleration force pushing into her and the scale. Okay, so during the deceleration of the elevator, the normal force on the feet of a passenger is going to be greater than her weight. Okay, and that makes sense. When you stop at the bottom of a floor, it feels like you're being pushed into the ground. Okay. Person who weighs W newtons stands on a scale in an elevator that is initially at rest. The elevator accelerates upwards to a constant speed, travels at that constant speed for some amount of time, then slows to a stop. Okay, which graph represents this? So we're looking at the weight over time. So when you're on a scale and the elevator starts going up, it's accelerating up. So that means the scale is going to read a let me see this screenshot here. Okay, so that means we're standing on the scale. Okay, we're going to have a weight here, and then you're going to, the elevator accelerates upwards to a constant speed. Okay, so at a constant speed, when you're at the constant speed, your scale should be the reading will be the same. Okay, so at a constant speed, zero acceleration, the weight is going to be your only force. So we've got to have one of the graphs where the weight is flat, at least at that constant speed, where it travels at that constant speed for some time. Because at that constant speed, you still have gravity on you, but no other acceleration. Okay, so it's got to be either this one or that one. So then the question is, okay, if you're moving at constant speed, what is your weight going to say? So if you try to imagine going down the highway and you accelerate up to 80 miles an hour and then you hit cruise control and then you sit there at 80 miles an hour, you don't feel like you're being pushed into your seat anymore when you're traveling at 80 miles an hour. You don't feel any heavier than you normally are. So it can't be this one where the weight is higher than at rest. So it's got to be this one where initially there's a increase in the scale reading. It increases until you stop accelerating, and then there's an impulse when you are doing that. And since it accelerates up to a speed and stops and sits there, yeah, it can't be the other ones. Okay, delete that. Next, when a net force is acting on an object, the object, when your net force is acting on an object, the object is accelerating. Net force means F equals ma. You got a net force, you've got to have an acceleration. Okay, next. According to Newton's second law of motion, F equals ma, when a net force acts on an object, the acceleration is, so you have F equals ma. So if you look at F equals ma, F equals ma, so the the acceleration is, okay, it is proportional to the force, okay, because they're both at the same level on either side of the equation. It is, so it's not inversely proportional to the force. It's certainly not unknown. It is not independent of the mass, and it's not zero. So it is inversely proportional to the object's mass. So what that means is the acceleration goes up, your mass has to go down. Or the more mass you have, the less acceleration you get. So they're inversely proportional to the mass. What that means, you increase mass, you decrease acceleration. Okay, the force of Earth's gravity pulls down on a snowflake as it floats gently towards the ground. What is the equal and opposite force during this interaction according to Newton's third law? So we've got gravity. We've got a pretty little snowflake here. Okay, and it's falling down, gravity. What is the equal and opposite force during this interaction of Newton's third law? So you got gravity pulling down. You're going to have some sort of air resistance floating to make it float gently. So, yeah, you're going to have the force of the air pushing back up on the snowflake. If it freely fell at acceleration, there would be no equal and opposite force. Let me think about that. Okay, so what is the equal net force during the interaction according to Newton's third law? Oh, I'm stupid. Jeez. Okay, let's go back to our snowflake. Why do I keep drawing it like that? Okay, what in the world? What does a snowflake look like? There we go. All right, what is the equal? Oh my gosh, I can't believe I just told you this. Okay, here's Earth. Here's the snowflake. Force of gravity is pulling down. What's the equal and opposite force? Okay, gravity is applying a force to the snowflake. The snowflake is applying a force to the Earth. So Earth is pulling on the snowflake is pulling on Earth. When we talk about Newton's third law, we're talking about that equal and opposite force. Not, sorry, I was thinking of the, why is the snowflake, I thought it was asking why is the snowflake floating gently towards the ground. No, Earth, Moon, Earth pulls on the Moon, Moon pulls on the Earth, those equal and opposite forces. Remember, F equals ma though. So in one case, you've got the force of the snowflake on the Earth, and then you have to use the mass of the snowflake. In the other case, you have the force of the snowflake on the Earth, and you have to use the mass of the snowflake. So mass of the snowflake is very small, so it's going to have huge acceleration. That's why the snowflake falls towards the Earth, and the Earth doesn't appear to fall up towards the snowflake. Okay, so that's what that one's about. Those are other forces in there, but they're not equal and opposite, the third law thing. Okay, so as a tractor pulls a plow across a field, it exerts a force on the plow in the forward direction. What is the equal and opposite force of this? So we've got our a plow, and here's the ground, and it's creating a channel as it drives through the thing. The plow exerts a force on the plow in the forward direction. What is the equal and opposite force? Okay, if the plow is plowing the field is going to plow the plow. Okay, so it could be the force of the ground pushing back on the plow. We've got a tractor, so let me make sure I just realized there's a tractor and a plow. So you have a tractor, and then it's pulling this plow behind it, okay? And the tractor is pulling the plow forward, okay? So in this case, the equal and opposite force would be the force of the plow pulling back on the tractor. Okay, so the tractor is pulling a plow across a field. It exerts a force on the plow in the forward direction. Then the plow is going to exert a force back on the tractor. Okay, so that's the equal and opposite force there. It involves the same objects. Okay, delete. 12. Student has drawn a free body diagram being of a box being pulled by a string down a rough incline. So there's friction. The force, the figure with the arrows, blah. Complete the diagram by labeling each. Okay, that's your normal force. That's your force of gravity. That's your force friction. And that would be the pull force. So we've got force of gravity would go down here. We've got force friction here. We've got the normal contact force there. And we've got the tension force, or the pull force, I guess they're calling it, here. Okay? Delete screenshot. Okay, so that's just helping you get familiar with the different forces. 4 fundamental forces. Choose the 4 fundamental forces. Strong, weak, gravity, and electromagnetic. So the first 4 that you see here. Strong is the strongest, gravity is the weakest, and the other 2 are in between. Okay? Let me just comment on this. Strong nuclear force, that's why protons are stuck together in the nucleus. The quarks are held together by the strong force. The electromagnetic force is photons. So light, radio waves, Wi-Fi is all electromagnetic. Gravity is gravity. And then weak nuclear force is what allows a proton to turn into a neutron in beta decay or other nuclear interactions like that. Neutrinos and stuff. Okay, so a space traveler weighs herself on Earth at a location where the acceleration due to gravity is 9.81 meters per second squared and finds a value of 569 newtons. What's her mass? Okay, so we're on Earth, and F equals ma, so we have 569 newtons is equal to the mass times 9.81, so you can solve for the mass there to figure out what her mass is given that force. Then she goes to a planet in a different solar system. It's a long trip, but she manages to maintain her physical condition, whatever, diet control. Yeah, okay. Thousands of years, dietitians hate her. The acceleration due to gravity on this planet is 13.7 meters per second squared, so it's a little bit higher gravity. She's going to feel heavier. What is the traveler's mass on that planet? Well, you figured out what the mass is here. Her mass is not going to change, so her mass stays the same. But the mass that you found there times 13.7 meters per second squared is going to be her new weight, her new mg, and you'll put that there. Okay. Next. 3 people pull simultaneously on a stubborn donkey. Jack pulls directly ahead of the donkey with a force of 77.7 newtons. Jill pulls with 99.7 newtons in a direction 45 degrees left. Okay, so you've got a donkey. Here's tail. Okay, one's pulling straight back with a force. One's pulling force. One's pulling force. 45 degrees. We've got 77.7 newtons. We've got 99.7 newtons and 111 newtons. Am I doing this right? 3 people pull on a donkey. Jack pulls directly ahead of the donkey. Jill pulls with 99 in a direction 45 degrees to the left. So let me draw this correctly. Okay, so we've got our donkey. Okay, Jack is going to pull directly ahead of the donkey. Let's make that pull force there. And then Jane is going to pull, actually Jill is going to pull 45 degrees to the left. So I'm going to, do they have a picture of this thing? Let me think about it. Okay, pull straight ahead, 45 degrees to the left, and 45 degrees to the right. So let's go with that. 77.7 newtons, 99.7 newtons, doesn't really matter. 111 newtons there, and 45. Okay, since the donkey is involved with such uncoordinated people, who can blame it for being stubborn? Okay, just wasted my time. Find the magnitude of the net force the people exert on the donkey. Okay, so the way this works, let me erase this and draw it a little bit better. Okay, so we've got one force, we've got another force, and another force. The total force is going to be this force plus the component of this force and the component of that force. That force, total force, sum of the forces in the y direction are going to be, if this is 45, then that's 45, everything's 45, 90s all around. Okay, then the sum of the forces in the y direction, for example, are going to be 77.7 plus 99.7 times cosine 45, or sine, doesn't matter, and then plus 111 times cosine of 45 degrees. You could do, adjacent over hypotenuse would get it over here, or opposite over hypotenuse would get it over here. When it's 45 degrees, you get the same thing. Okay, so I'm not paying attention to that. Some of the forces in the x, then you do the same thing, except there's no force from Jack in the x direction, and Jill's possibly going to be 0. Do we know that? Well, what direction is the net force? So we don't know if the sum of the forces in the x add to 0. So we're going to have 111 cosine of 45 minus 99.7 cosine of 45, because we want this minus that. Okay, if that's not 0, I'm not going to calculate that. If that's not 0, then you're going to have a net force vector in the x or the y direction, and then we've got a net force in this direction. So then let's say, I haven't calculated this, so I don't know. Let's say the net force is somewhere there, okay, because we've got an up component, but then Jill's pull is a little bit stronger. So our net force vector is here, okay? Our net force vector is there, and that is going to be, your net force, okay? So that's the direction of it. So then you'd have to determine the angle here to get the direction of it. Magnitude is easy. Just do the square root of a squared plus b squared is c squared, or, whatever. All right, and the direction of the net force, then find that angle with respect to the normal there. Okay, so that's just vector stuff. Delete. Next, analyze the free body diagrams and place them in order indicated by the magnitude of the forces. Okay, so what we're doing here, which one has the smallest, which one has the largest net force. So this is easy. You just take your pen and you head to tail everything. Okay, so we've got A plus B, for example, plus C, and then plus D. It's going to be 1, 2, 3, 4, 5. It's going to be 1, 2, 3, 4, 5, something like that. So then the net force vector of here is there. Okay, let's do the next one. F plus E plus G. So that one looks 0 to me. F plus E, 1, 2, 3, 4. 1, 2, 3, 4, 5. Yeah, so if you add those three vectors together, you get 0. Okay, and then this vector plus that vector, your resultant is that vector. And then this one looks tricky. I'm going to go with this one plus that one plus that one plus that little guy plus that one. So it looks like that one is the net vector there. So it's going to be a close one between here and here, but if you do it a little more carefully, then you'll get that right. Okay, let's see. It's always a good idea to get some sense of the size of the units. For example, the mass of an apple is about 100 grams, whereas a bicycle is about 100 times more massive than at 10 kilograms. Estimate the masses of the objects. Okay, so a dime, I don't know, maybe a gram. A smartphone, not 10 kilograms, maybe 100 grams. An adult male, 100 kilograms. That's like a 200-pound dude. A college physics book, 2.2 pounds. That's what 1 kilogram is. Yeah, maybe 1 kilogram. Small car, about maybe 1,000 kilograms. A ripe banana, maybe, I don't know, 10 grams, maybe 100 grams. I don't know. Think about it. Okay, clarinetist setting up for performance grabs his 3.490 kilogram clarinet case, including the clarinet from the top of the piano, and carries it through the air with an upward force of 32.5 newtons. Find the case of vertical acceleration. Okay, so what this one is you got a clarinet in a case, lift it up with a weight, with a force of 32.53 newtons. But there's also a weight down of 3.490 kilograms times 9.81 meters per second squared. Okay, so that's the force of the weight. So the sum of the forces in the y direction are going to be 32.53 minus whatever your weight is, and then that's going to equal mass times acceleration. So then you divide by the weight of the thing back out there to get your acceleration, vertical acceleration. Okay, boom. Simple elevator ride could teach you quite a bit about the normal force. You'll never ride an elevator the same, trust me. There are 3 different scenarios given detailing the rider's experience in an unnamed hotel. Why is it unnamed? I don't know. For each scenario, calculate the normal force acting on the rider if his mass is 73.6 kilograms, acceleration of gravity. So you're going to have the normal force. So you're always going to have the weight is equal to mg. The normal force is going to equal the weight and then either plus or minus ma, whatever acceleration the elevator has. If the acceleration is up, then you get heavier, so the normal force gets bigger. If the acceleration is negative, then you're lighter, and then your weight, normal force is less than your weight. Okay, so what you have to do here, if the elevator is at constant velocity, then the normal force is just mg. If the elevator is moving upwards, it's a positive acceleration, so it's going to be weight plus m times 4.84 meters per second squared, so it's going to have a higher normal force than normal. And then when the cable breaks and it accelerates downwards at this, then you're not going to have a normal force. You're just going to be in free fall. Okay, 11 kilogram objects is the given xy acceleration components, ax and ay. What is the magnitude of the net force acting on the object at t equals blah? Okay, this one's trying to make you go crazy, I guess. Okay, don't overthink it. What's the net force? F net is equal to ma. Okay, what do we have to do? We have to find F net. What is F net? ma. These are vectors. So this is going to equal m times the square root of ax squared plus ay squared. Okay, because we want to get the resultant vector of ax and ay. So you got to calculate what ax is at t equals 4.47. So this is imagining an acceleration that is time dependent. Your acceleration is changing. Who cares? They just threw in some crazy equations for you. So just plug in 4.47 there to solve for what ax is, solve for what ay is. Plug them in there because that's your x and y component of your acceleration. And then the magnitude of that is a squared plus a squared, ax plus ay squared, square root. That'll give you the magnitude, and then you multiply that by mass to get the force. What is the angle theta of the net force at the same time? Give your answer as a number of degrees counterclockwise from the x-axis. What is the angle of the net force? So yeah, just do you've got ax, ay. You can use tangent of theta is equal to ax over ay, and then take theta is the inverse tangent of ax over ay, for example, or ay over x, or whatever the thing works out to be. So that's, again, trying you to get to understand the relationship between the xy components and the angles between them and how where's the right triangle type of stuff. Okay, next. 3 crates with various contents are pulled by a force of 3,515 newtons across a horizontal frictionless roller conveyor system. The group of boxes accelerates at 1.686 meters per second squared to the right. Between each adjacent pair of boxes is a force meter that measures the magnitude of the tension connecting the rope. Between the box of mass m1 and mass m2, the force meter reads. Okay, let me see if I can get to it. Well, I can't. between, okay, F12 is 1374 newtons. Between the box of mass M2 and the box of mass M3, the force meter reads 2,225 newtons. Assume that the ropes and the meters are massless, whatever. Okay, what is the total mass of the 3 boxes? What is the mass of each box? Okay, so I can screenshot this there now. I was worried I wasn't going to be able to see everything. Okay, so we got a pull force. Okay, we've got 3,515 newtons of pull force, and we are told that it accelerates at 1.686 meters per second squared. So that pull force is equal to MA. What is the mass of all 3 boxes? Okay, that's easy. It's just, M is 3,515 newtons. The total pull force divided by the acceleration, 1.686 meters per second squared. Boom. Total mass of all the boxes. Done. Okay, then the question is, what's the mass of each box? Well, you know that this force causes this acceleration for all 3 masses. The key here is they all accelerate at the same rate. Since they all accelerate at the same rate, then you can say that F12 is equal to M1, because that force is only accelerating that box. So F12 is M1 times A, and so that means M1, the mass of that box, is 1,374 newtons divided by the acceleration, 1.686 meters per second squared. Okay, and then that gives you M1, and then you know what the total is, and then you can use F23 is going to be M1 plus M2 times A is equal to 2,225 newtons, because this force is the result of pulling both M1 and M2 masses. But you know what M1 is now, so you can plug M1 in there and solve for what M2 is. And then when you do that, then you get what M2 is, and then you can get M3 by just subtracting those 2 from the other total. Okay. A person whose mass is 108.5 kilograms steps on a mechanical bathroom scale placed on an inclined plane. That sounds dangerous. That's how people die, seriously. Okay, on a inclined plane that makes this angle. So let's go look at this. Person stands on a scale that's at a slight incline. So there's the person on this scale. Alpha is 16.3 degrees. With the horizontal, what is the reading on the scale? Okay, so that would be your weight. Mg sine theta is going to be your the down component, and mg cosine theta is going to be the component that the normal force is going to have to handle. So there you go, mg cosine theta. Delete. An Atwood machine consists of 2 masses hanging from the ends of a rope that passes over a pulley. Assume that the rope and pulley are massless and that there is no friction in the pulley. If the masses have the values of blah, blah, find the magnitude of acceleration. Okay, so basically what you have is weight here and weight here. Okay, and they actually, because of the Atwood machine, they balance each other out, or they at least they work against each other. So you're going to have M1 times G is going to be the force of gravity here, and then that minus, because you're going to have a tension force up here, the tension force here, we could call it minus tension, and let's see, 2 masses, assume the rope and pulley are massless, no friction. If the masses have this, find the magnitude of their acceleration, A, so they are accelerating. So mg minus this tension force are going to equal ma, and then the other mass here, m2g minus the tension force here is going to equal ma, m1a and m2a. Okay, so the key here is that this tension force is just equal to m2g. Okay, so then you can, say that since they're both going to accelerate since they're connected at the same rate. So your acceleration you can solve by setting up that equation. Okay, and then just, solve for what you need to solve for. We've got the masses m1 is 20 kilograms, m2 is 10 kilograms, and then you can just plug all that in and figure out what the tension is, and then figure out what the acceleration is. 2 equations, 2 unknowns. Okay, delete the screenshot here. Delete. Okay, there we go. Okay, we got an object hanging in equilibrium at the end of a rope. Jeez. Okay, take it as massless. Okay, the rope's massless. Wind pushes on the object. Find the magnitude of the tension in the rope. Okay, there's our tension in the rope. What else do we have? We've got the weight here and the wind here. Okay, so how you do this? That's the tension in the rope. The tension in the rope is there's an x component of the tension and a y component of the tension. The x component of the tension is canceling out the wind. The y component of the tension is canceling out the weight. So if you can figure out the weight, that's the y component. If you can figure out the wind, that's the x component. Then tension is the square root of x squared plus y squared. Okay? So that's what we're going to do here. We've got the mass of the object is 2.7 kilograms, so weight is 9.8 times 2.75. There's our weight force. That will be newtons. And then our wind force is 17.5 newtons. Okay, so this vector plus that vector equals that vector, and this vector and the tension vector equal each other, because that's what tension is doing. It's absorbing both of those forces. So then you just solve for the tension force, and then to get the angle, you can do whatever sine, cosine, and tangent to get it, because you know what the every component is at that point. Okay, delete. A crate hangs from a rope that is attached to a metal ring. The metal ring is suspended by a second rope that is attached overhead at the 2 points as shown. What is the angle theta if the tension in the rope is 1 is 1.3 times the tension in the rope 2. Okay, so we've got our box here, we've got our weight, we've got our T, what is rope 2? Rope 2 is, so that's T2, and that's T2, I guess. Suspended by a second rope, what is the angle of the tension? Okay, so rope 1, okay, so we've got a weight. Oh, geez, okay. Let's clean this up a bit. Okay, so we're going to have a weight down here, and a tension in the rope there, and a tension in the rope there, and a tension in the rope there, and a tension in the rope there. Okay, we've got the metal ring, and we don't have a mass or anything. We want to know what is the angle if the tension in rope 1 is 1.3 times the tension in rope 2. Okay, so the tension in rope 2 is here, T2. Let me think about the force. We can think about a force here and then having 2 components like that. Okay, and then our rope 1. So what is actually happening here, right? This ring here is supporting all of this weight. So we're going to have a tension in that rope, and we're going to have a tension upwards that cancels that out, and then we're going to have 2 tensions here that cancel themselves out. So we've got these 3 components there in this angle here. So what if T, so we need to just figure out our components, okay? And so we say that this is T2, and presuming T2 is the same because they're symmetric, and this is T1 where the rope is, and we can say that T2, if that's our angle, opposite T2 sine theta is equal to T2 sine theta opposite over hypotenuse, that would be Tx, T1x, T2x, T1x, okay, and then T2 sine theta is equal to T2x. They're the same component, equal and opposite, and then T2 cosine theta. So we're going to have 2 T2 cosine theta is equal to T2 cosine theta is equal to T2y. And yeah, these are going to be equal and opposite. And then T2 cosine theta is equal to T2y. So we're going to have two y components adding up. So the total force in the y direction is going to be 2 T2 cosine theta minus T1 is equal to 0 because they're suspended. So we're going to have 2 T2 cosine theta is equal to T1. And then we know that this is 2 times T. So we know that T1 is equal to 1.3 T2. Okay, so we can say T2 cosine theta is equal to 1.3 T2. And that's going to cancel out the T2's. So then cosine of theta is equal to 1.3 divided by 2. And then you can solve for what theta must be if that's the ratio of them. Okay, that's a tricky problem. Delete. Suppose a gymnast climbs a rope. What is the tension in the rope if she climbs at a constant speed? If she climbs at a constant speed, that means the only acceleration is due to gravity. So the only tension in the rope will be due to her weight, which would be mg. And if the tension in the rope, if it's accelerating upwards, then the tension will increase by that ma amount, by mass times acceleration. That's an extra force that you're adding. So then you would add mg plus this new force here, ma, this new acceleration there, and then that would increase the tension in the rope. Okay. Oops, I didn't want to do that. Delete. As a hiker in Glacier National Park, you look for a way to keep bears from eating your food. You find a campground that is near an outcropping of ice. Part of the outcropping is a slope, blah, blah, blah. You decide to place your food and hang it over the cliff. You put all your food into a sack, and then you have rocks on the other end, blah, blah, blah. You have 23.5 kilograms of food left over, so you put 23.5 kilograms of rocks in an anchor bag to balance it out. What happens when you lower the food bag over the edge and let go of the anchor bag? The weight of the bags and the rope are negligible. The ice is smooth enough to be considered frictionless. Okay, so what's going to happen is you can already tell if you put 23.5 kilograms in both of these things. We've got 23.5 kilograms of full weight here, but we don't have the full weight here. We have mg sine theta for that force, and we've got mg for this force. Which one of these is bigger? This one. Okay, so you don't want to, well, okay, if that's your force here, you've got a force here that's less than this force. Okay, so what's going to happen in my view right now, I would think that this would not be good enough, and the bag here will just start to accelerate because it's got a bigger force. You're going to need more mass here to deal with it. So let's see what we get. So some of the forces here, if we add up all our forces, we're going to have mg, which is this weight, and then minus, there's going to be a force pulling back on it from gravity on this guy, which turns this force of gravity here is the same as this tension force there. Okay, so then this object, mg, minus mg sine theta, which will be the component of gravity pulling down this way, that depends on, there's your weight, and you want the component g sine theta of that. Okay, and what do you get if you do that? That is obviously not 0, so yeah, we're going to have mg minus mg sine theta. Sine theta is a number between 0 and 1, so we're going to have mg minus a number less than mg, so we're going to have a net force this way, and so we're going to have net acceleration of m1, well, we're going to have 2, it's the same mass, so 2m times a. So if you divide by 2m, then m's cancel, and you get g times 1 minus sine theta. G over 2 times 1 minus theta is your acceleration, which is pretty cool. Okay, so what's going to happen? The anchor bag is on a slope, so the food bag will drop, pulling the anchor bag up. Bingo. Okay, so that's what's going to happen. What will the acceleration be? So that's what I just calculated. Okay. Done. Okay, laboratory concept, static equilibrium using an apparatus called the force table. Yeah, this is usually something you do in a lab. Force table consists of round, level platform, blah, 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 mass of this to calculate the mass M3 in order to balance everything out. Okay, so this was common, very typical problem. Okay, you've got weight, weight, weight. Forget about this. Think about it from the top view. You have A, B, and C vectors. Okay? X components cancel out. Y components cancel out. Figure out your forces. You got your weights, turn them into forces. Figure out your X and Y components of your forces. Solve for what the new force is to balance everything out. And then divide by G, and you'll get your mass. Okay? And then your angle is what you need to get your vectors to work out. So, for example, we've got M1 is, so theta 1 is, so if we keep that as the top, call theta 1 26.5 degrees. Imagine that's just a force, M1 times G. And then M2 is located at 291, so that's, if this is 0, then this is 90, that's 180, that's 270, so 291 is going to be, somewhere over here, and you're going to have M2G there. So then you're going to want to figure out the X component. That X component should cancel out. If they don't, you need the X component of M3 to take care of that difference. Y component, and then you're going to need the Y component of M3 to balance those two out, and then let's say this one's slightly bigger than that one, so we're going to have an X component, so your net M3 vector might be there. That's going to be a force, F3, divide that by mass, by G, and then that's going to give you the mass M3, okay? Next one, cube of mass blah is sitting on top of a second cube of the same size and mass 1.1 kilograms while both are in free fall. Ignoring any air resistance, what is the magnitude of the normal force with which the bottom cube is acting on the top cube? Okay, so we've got one mass on top of another mass while both are in free fall. What is the magnitude of the normal force with which the bottom cube is acting on the top cube? Well, if they're both in free fall, you tell me. A block of mass m with a given initial speed slides down a rough incline with constant speed. If a similar block has a mass form were placed on the same incline with the same initial speed, what would happen? Okay, so we've got, it's a rough incline, okay? Rough incline. So if this were frictionless, we'd have a different scenario on our hands because the only thing that causes an acceleration is g sine theta. And you would know that mg sine theta is the force of gravity down the slope, and that is equal to ma. So the mass is canceled, so your acceleration is independent of the mass. So it shouldn't be, the mass will not increase, the increase of mass will not make the thing fall faster. But we have a problem because it's on a rough surface. So if we increase the weight, we increase the normal force. If we increase the mass, we increase the normal force. So that means we're going to increase the force of friction. So by increasing the mass, we increase the force of friction. So it will have a, it will not be able to speed up the same. And it's sliding down with constant speed. If we put 4 times the mass on there with the same initial speed, it's going to slow down, right? Because it can't keep up that same speed. So it's going to slow down. It'll decelerate. It will, accelerate down the incline significantly less than, it could not move. It could slide at constant speed. Given initial speed slides down a rough incline with constant speed, you increase the mass. It's gonna, it'll stop. It's gotta decelerate, right? That would be my thought. Okay, think about that one more. I'm tired. Delete. Next one. Two solid rocks have the same length and are made of the same material with circular cross-sections. Rod 1 has radius R1, rod 2 has radius R2. If the compressive force applied to both rods, their lengths are reduced by delta L, respectively. Okay, so you're going to use your F over A is equal to 1 over Y delta L, let's see, L, yeah, delta L over L0. I think that's the formula, close enough. You'll look it up. Okay, they have the same length, same initial length, L0, same cross-section, so they have the same area, same circular cross. It's a circular, so not the same circular crosses. Okay, so different circulars. So they have different areas, okay, because their radii are different. So what you're going to do is, this is a typical type of problem. You're going to divide the same thing. Okay, 1 over L. You can divide equations. Did you know that? Divide by L0. Okay, so all this stuff is going to cancel out. Did I do 1 over L? 1 over Y. All that stuff's going to cancel out. You're going to apply the same force. The difference here is that you're going to have pi R1 squared for the circular area of the one, and then for the other one divided by pi R1 over 2 squared. And that's going to be the ratio delta L over delta L. Okay, the pi's are going to cancel. The R squareds are going to cancel. You're going to have 1 over 1/4, so it'll be 4 times it'll either be 4 times or 1/4, depending on when you set this up and solve for this correctly and do a better job than me. Okay, well, that's your typical thing, divide two things together. Force exerted on this, motions caused, right, you got a friction force or whatever like this. To describe the relationship between stress and strain for the book, in this situation you would use, okay, so you're going to use the shear modulus because you're applying a shear force, causing it to distort, okay? We are not using the other forces. There's no other deformation here that I can see. Oops, delete. Okay, what are the correct units for stress? Stress equals Y times strain. So stress is force per area, which is newtons per meter squared, okay? Force per area. A wire is stretched just to its breaking point by a force F. A longer wire made of the same material has the same diameter. The force that will stretch the wire to the breaking point is, okay, so again, take that equation, do the same thing, the modulus. When tension is applied to a metal length L, it stretches by delta L. If the same tension is applied to a metal wire, same material, same cross-sectional area, but length is 2L, how much will it stretch? Okay, we'll just put 2L in there and figure out what delta L is. Steel cable lifting a heavy box stretches by delta L. In order for the cable to stretch by only half of delta L, about what factor must its diameter increase? Well, it's a box, so the area goes like length times width. So if you want to increase the diameter so that you reduce the area by the stretch by half, you need to reduce the area by half. So so anyway, what factor must its diameter increase? You want to make sure that the area just increases by half, okay? So square root of a half, whatever that is. A box of mass M is pulled up a ramp that is inclined at this angle. Coefficient of friction is this. The rope pulling up thing. The box accelerates up the ramp at this rate. Calculate the tension in the rope. Okay, so we've got a thing here. The acceleration is upward. So we're going to have weight here, and we're going to have mg sine theta in this direction. So that's minus, and then plus the tension in the rope, which is going to be in this direction, and that's what's going to be pulling the thing up. But then we're also going to have minus the mg cosine theta times mu k. We're going to have the normal force here, and we're going to have a force of friction, which is opposing the motion. So that's going to work together with gravity, in fact. And then that is going to equal ma. Okay, so then the acceleration here is given, and so we're going to say the tension then is going to be ma plus mg sine theta plus the mg cosine theta mu k, the force of friction. Okay, And that makes sense. All those forces should add together to put stress on the rope. Two blocks are connected by a massless rope over a massless frictionless pulley as shown. The mass of block 2 is M2 is this, and the coefficient of kinetic friction between block 2 and the incline is 0.2. The angle theta of the incline is 33.5 degrees. If block 2 is moving up the incline at a constant speed, what is the mass of block 1? Okay, so constant speed means no acceleration, so this is actually the same as if they were sitting at rest, okay, which is a little bit of, might be a little bit confusing to you, but even if they're moving at constant speed, that would be the same thing as if they're sitting at rest with each other. The forces will be balanced on them. So you're going to have the weight here, and you're going to have the weight here. That's the only two forces. So weight 1, and then you'll have a tension force here, but that tension force will be the same as this tension force, and that tension force will be the same as the weight here. So weight 1 minus weight 2 is going to equal MA. We know this is M1 G1 minus M2 G2, not G2 and G1, is equal to, in this case, the mass is M1 plus M2 because they're connected times the acceleration. Okay, and then the weight here that we care about for W1 is just mg. For M2, it's mg sine theta because it's the component of the weight that's doing the acceleration. Okay, so then you can figure out what, oh, I'm sorry, acceleration is 0, haha. So you're going to have m1g minus m2g sine theta equals 0. And, oh shoot, we've got friction. Sorry, let's do all this again. We get mg, this force minus that force, and then also if the block 2 is moving up the incline, then that means the force of friction is that way, negative. So we're going to do a minus mu k times m2 cosine theta times g to get the force of friction. Okay, then that equals 0. Good. What is the mass m1? And we know what m2 is. Okay, so now we've got everything we need to solve for m1. All right. Book is placed on a flat desk. Book coefficient is this and that. How much force is needed to begin moving the book? This problem's at the very end, of course. Simple one. You got a book on a desk. Coefficient of static friction is, so mu sub s is 0.442. How much force is needed to begin moving the box? That's the force of friction. That's mu sub s times the normal force times mg. So 2.03 kilograms times 9.8 times 0.442. That's the static friction. Yep, and solve for that. How much force is needed to keep it moving? Replace that with mu k, and you're done. Okay. A heavy sled is being pulled by 2 people. Oh, ho, ho, this looks tricky. There's an angle here. Blah, blah, blah. The combined mass of the sled and its load is this. The ropes are separated by an angle of 29 degrees, and they make an angle of 31 degrees with the horizontal. Assuming both the ropes pull equally hard, what is the minimum tension in the rope required to get the sled moving? Okay, so we've got a lot going on in this problem. We've got a sled that's 381 kilograms. So we're going to have a normal force of mg. There's our normal force, which means we're going to have a force of friction against them, which is, so a heavy sled is being pulled by 2 people as shown in the figure. The coefficient of static friction is this, kinetic friction is that. The combined mass of the sled is this. 2 ropes are separated by this angle and this angle. Assuming both ropes pull equally hard, what's the minimum tension required to get the sled moving? Okay, so then we're going to have a force of static friction, which is mu sub s, times the normal force, mg. So we need to have enough tension in the rope to apply this net force in the x direction. Okay, so we've got to apply a force in the x direction, right, that is equal to mu sub s. So that means we have to figure out what components this is in order to get that. Okay, so that's a tricky problem, but we just use our angle here and figure out the tension component in the x direction, and then 2 times that because we've got 2 people, and then first we find the force of friction, then we find the x component, then we use the angle to find the total resultant, and there's going to be 2 of these tension forces. So the minimum tension is going to be in terms of 1 rope, yeah. So 1 of the tensions, because you're going to have 2 of them since there's 2 ropes, is how I understand it. Okay, and then when you do that, once it starts moving, you're going to have that same force. If you maintain that same tension, then mu sub k will be lower, and mu sub k is lower. So that means you're going to have all this stuff. The tension in the x direction minus the force of kinetic friction is going to equal ma, and then you can solve for your acceleration. Okay. Next, disc between vertebrae and the spine subjected to the shear force. Okay, you got a shear force for shear deformation, then you know that you need to use the shear modulus and use the shear modulus equation. And then you've got your shear force of 575 newtons. You've got a shear modulus there, and you've got the solid cylinder with this height and diameter, so then you solve for the area of that thing. Okay, femur bone of the human leg has a minimum effective cross-section of 3 centimeters squared. How much compressive force can it withstand before breaking? Okay, if the ultimate strength is 1.7 times 10 to the 8 newtons per meter squared, then that's your force per area. Then you can solve for the force necessary to apply that force per area using your regular stress versus strain equation. Okay, vertebrae subject shearing force to this, shear minus this, yeah, so let's just plug and check again. A steel cable supports an actor as he swings onto the stage. The weight of the actor stretches the steel cable. To describe the relationship between stress and strain for a steel cable, so this we're pulling on a cylinder, we're stretching a cylinder, so you'd want to use the Young's modulus for that type of deformation. Okay, bye.